Just a few days ago, Google DeepMind unveiled something truly game-changing, Alpha Evolve, a cutting-edge coding agent powered by Gemini. Now here's the thing. Most people still don't fully realize just how big this is. Why? Because for the first time, we're watching AI step into a real-world, high-impact role. Not just running code, but actually accelerating the way AI itself is developed. It's like AI helping build even better AI. And that kind of rapid feedback loop? It's already shaking up the entire tech world. In this video, I'm going to break it all down for you. What Alpha Evolve actually is, how it works, and why it's such a groundbreaking leap in AI. At its core, this is an agentic system, which means it can operate independently and intelligently. And what it's done so far is nothing short of incredible. It's designed faster matrix multiplication algorithms, tackled open mathematical problems, and even made huge strides in optimizing data centers, chip design, and AI training across Google's infrastructure. But here's the real question. We know what it does. Now let's dive into how it does it. Let's take a closer look at how Alpha Evolve actually works, starting with a high-level overview. It all begins with the human. The human defines the what. Basically, what are we trying to achieve? What's the goal? How do we measure success? You provide some initial code or background information, and from there, it's up to the AI to figure out, how can we make this better? The system is built around a powerful loop. At the core, there's a program database, a kind of giant memory bank that stores every version of the code the AI has tried, along with performance results. Next, there's a prompt sampler. It pulls useful pieces of past code and ideas from that database, then formats them into a message for the AI to work with. From there, the language model steps in. It reads the prompt and starts generating new, improved versions of the code. Then comes the evaluation stage. A pool of evaluators runs the new code, scores it, and asks, is it better? Is it faster? More efficient? If the answer is yes, that version goes back into the database, and the cycle repeats, over and over again. And what do you get at the end of it all? A smarter, faster, more optimized version of your original code, refined through non-stop trial, testing, and intelligent improvement. This feedback loop keeps running, constantly pushing your code to the next level. Now here's the wildest part of all this. Alpha Evolve isn't just a flashy demo Google rolled out to impress the AI world. They've actually integrated it into their core systems, and it's already making a serious impact across Google's entire infrastructure. For example, take data center optimization. Google uses something called the Borg scheduling system to manage job assignments across its massive network of servers. But sometimes, resources like memory or CPUs get underutilized. Alpha Evolve stepped in and discovered a new, simple heuristic for job scheduling. And just like that, it helped recover 0.7% of compute resources across Google's global fleet. And that's not just a one-time win. Post-deployment data shows this improvement is consistently saving compute power. Then there's hardware optimization. Specifically, the design of Google's TPUs, custom chips built for AI training. Alpha Evolve modified the Verilog code, a hardware design language, stripping out unnecessary components. The result? Lower power consumption and fewer errors in critical TPU operations. Google engineers reviewed and validated the changes, and they're already being implemented into future TPU designs. But it doesn't stop there. Alpha Evolve also tackled software efficiency, helping optimize the training of Gemini, Google's own foundation model. It improved performance at the kernel level, streamlining how matrix multiplications are handled. The outcome? A 23% speed boost in key kernels and a 1% reduction in total training time. A huge deal at Google scale. According to their official paper, the tiling heuristic discovered by Alpha Evolve has already been deployed in production, enhancing Gemini's training efficiency moving forward. So what does this all mean? In just 3 major areas, data centers, hardware, and software, Alpha Evolve has delivered real, measurable improvements. But now, think about the bigger picture. What happens when an efficient AI starts building even more efficient AI? That's the point where progress could start compounding fast. And the future of AI development might just accelerate beyond anything we've seen before. Now here's the wildest part of all this. Alpha Evolve isn't just a flashy demo Google rolled out to impress the AI world. They've actually integrated it into their core systems, and it's already making a serious impact across Google's entire infrastructure. For example, take data center optimization. Google uses something called the Borg scheduling system to manage job assignments across its massive network of servers. But sometimes, resources like memory or CPUs get underutilized. Alpha Evolve stepped in and discovered a new, simple heuristic for job scheduling. And just like that, it helped recover 0.7% of compute resources across Google's global fleet. And that's not just a one-time win. Post-deployment data shows this improvement is consistently saving compute power. Then there's hardware optimization. Specifically, the design of Google's TPUs, custom chips built for AI training. Alpha Evolve modified the Verilog code, a hardware design language, stripping out unnecessary components. The result? Lower power consumption and fewer errors in critical TPU operations. Google engineers reviewed and validated the changes, and they're already being implemented into future TPU designs. But it doesn't stop there. Alpha Evolve also tackled software efficiency, helping optimize the training of Gemini, Google's own foundation model. It improved performance at the kernel level, streamlining how matrix multiplications are handled. The outcome? A 23% speed boost in key kernels and a 1% reduction in total training time, a huge deal at Google scale. According to their official paper, the tiling heuristic discovered by Alpha Evolve has already been deployed in production, enhancing Gemini's training efficiency moving forward. So what does this all mean? In just 3 major areas, data centers, hardware, and software, Alpha Evolve has delivered real, measurable improvements. But now, think about the bigger picture. What happens when an efficient AI starts building even more efficient AI? That's the point where progress could start compounding fast. And the future of AI development might just accelerate beyond anything we've seen before. One of the most jaw-dropping breakthroughs Alpha Evolve pulled off was in matrix multiplication. And if you're into AI or computer science, you know just how big of a deal that is. Matrix multiplication is a core operation used in everything from training neural networks to graphics rendering, physics simulations, and search algorithms. The goal? Multiply 2 matrices as efficiently as possible, because even tiny improvements here can lead to massive gains at scale. Now, back in 1969, a mathematician named Volker Strassen made headlines by finding a way to multiply 2 by 2 matrices using 7 multiplications instead of the usual 8. That small tweak was revolutionary, and when you scaled it up, it allowed 4 by 4 matrices to be multiplied using 49 multiplications. For 56 years, no one managed to beat that. Until Alpha Evolve came along, it found a new method to multiply 4 by 4 matrices using just 48 multiplications, finally breaking a decades-old record. And here's the wild part. It did this without any human-written mathematical proofs up front. It simply ran evolutionary-style searches, tested the outcomes, and kept only the best-performing results. In other words, Alpha Evolve created an AI-discovered algorithm through trial and refinement, a kind of meta-innovation where the AI invents new ways to solve problems we thought were already optimized. And this isn't just a math flex. Models like Gemini, GPT, and Claude perform billions of matrix multiplications during training. So even a small boost in efficiency can result in huge compute savings. In fact, this particular discovery contributed to a 1% reduction in Gemini's overall training time, a significant improvement at Google's scale. Now let's hear directly from some of the researchers behind this breakthrough, the minds who helped make Alpha Evolve a reality.
That actually there is a faster way of doing it. And so already for multiplying 2 by 2 matrices, so the smallest non-trivial case, if you do it the high school way, you need to do 8 multiplications because there are 4 entries in the output matrix. It's a 2 by 2 matrix, and each scale, like each inner product, requires 2 multiplications. So 4 times 2 is 8. But Strassen, he came up with this ingenious way of making a procedure that only requires 7 multiplications. Even though the matrices are very small, the space of possible algorithms, how you could multiply them, is just completely immense. So computationally, there is just no hope at all to do this exhaustively. Okay, so for 3 by 3, the best algorithm is using 23. That's at least better than the algorithm you get taught in high school, which would be 27. So at least there is some progress on making it better. But then for 4 by 4, which is like the next size, the best algorithm that had been known was just apply Strassen's algorithm recursively twice. So because Strassen is for 2 by 2 matrices, what you can do if you have a 4 by 4 matrix, you consider it as a block matrix of 2 by 2 blocks, and then each block itself is a 2 by 2 matrix. So you can do Strassen twice. And because Strassen needs 7 multiplications, if you do it twice, you will get 7 times 7, 49 multiplications. So for the so this was the only way known how to multiply 4 by 4 matrices in a fast way, like using 49 multiplications just to Strassen twice. And this has been the kind of the situation since 1969. For the usual case of matrices that have arbitrary numbers in them, still nothing better was known than doing Strassen twice using 49 multiplications. So we're like really excited when we used AlphaEvolve in this setting. We actually didn't even hope that it would find something better than 49 because we were trying for so long with Alpha Tensor. We just ran it for completeness because we wanted to have this, this table in the paper that we actually have, that we tried on all the sizes up to 5 or 6, and remarkably it found a faster algorithm which uses 48 instead of 49 multiplications. When one of my teammates messaged on the channel that, oh, it seems like we have this result, I just couldn't believe it. Like, let's triple check it. But then it was indeed correct. If you find an algorithm that can multiply complex matrices, you can also apply it to real matrices. It's just a generalization. So what's kind of cool here is that let's say you care about multiplying real matrices, which is what you care about when you train neural networks, let's say, a very common use case. A priori, you might just look for an algorithm that uses real numbers. But you can say that, oh, actually, what if we look for a complex algorithm, which a priori you would think, well, that's a more difficult task because that algorithm would actually apply not only to real matrices, but also to complex matrices. But by making the task more difficult, actually AlphaEvolve was able to find an algorithm that uses complex numbers and therefore applies to both complex matrices and real matrices. So we are presenting a coding agent, which we called AlphaEvolve. And what this agent is able to do, it's able to design quite advanced algorithms. And when I say advanced, I mean it's algorithms that are able to make new discoveries in the sciences. And we have quite a few examples in mathematics and computer science in this paper. Or on the practical side of things, they're able to speed up really already heavily optimized pieces of important computational infrastructure within Google. You build some tool for like scientific purposes, and then out of the box, you can do it, apply it to real world challenges and have so much impact. Like usually there is an entire body of work, research work that needs to happen to translate a scientific technology into something that's actually useful in the real world. Like usually there is so many challenges you have to tackle, and here there is a tool which out of the box at the same time is able to make new discoveries on mathematical and scientific problems, and at the same time is able to discover algorithms that you can directly deploy into Google's like critical compute stack. So that's something I certainly hadn't experienced before and maybe wasn't expecting, to be honest.
Such that we can exactly verify in exact arithmetic that they're correct. And then we'll have this quantization loss, which will drive the solution towards that set of integers, for example. And then, normally we as humans would only try like, tuning the weight of that quantization term, or maybe in the worst case, like the schedule of the weight, like maybe you will have less of it in the beginning and then like more of it in the end. But what AlphaEvolve did was producing like a whole kind of time evolving shape of the quantization loss, which kind of again makes sense, right? Like you wouldn't say that it's not going to work, or otherwise you wouldn't looking at it, you wouldn't say that, oh, this is amazing, this is like definitely going to work. But the thing is, like, you wouldn't even try it as a human because it's like so complicated that you would never even think about tuning such a complicated like kind of function which changes shape over time with iterations.
Depending on the starting solution, there's a kind of cone of things, of leaps that we can make. And can you speak to any examples where the system made really imaginative leaps?
Yes. So I can talk to that. And indeed, you identified one interesting feature of the system, which is that depending on what you tell it at the beginning, you can guide the process. So if you give it fairly specific instructions or you ask the system to start from a specific type of solution, then what it will usually do, it will like squeeze out the juice of that idea that you gave it or squeeze out the juice of that initial solution, see how it can tweak it and bring it to its maximal potential. But by default, you would start with a solution that's like really, really empty. So you give Alpha Evolve a code skeleton where all the functions are like almost an empty implementation. You just like return zero or return false and so on, and you just let it to be completely creative. And so it just has to rely on like its background knowledge of the base LLMs, and it can explore in all possible directions. And the evolutionary algorithm makes sense that you preserve the diversity as you keep doing the exploration.
In an ideal world, what we want algorithms to do is compose abstract basis knowledge. So knowledge which is as far down the stack as you can possibly do to sort of increase our flexibility. And we should just bring in how you modeled this representation. So you had these different approaches. You could directly model the solution. You could model a constructor function. So, you're actually learning a function which itself constructs the solution. You could be learning a search algorithm, which is what you did with the matrix multiplication. And you also spoke about co-evolution as a possibility. So this is mind-blowing in the sense that there's some human design and intuition in how you design the optimization target, but there's this ambiguity in the ways that you can represent so many of these problems and how they relate to each other.
And one particular example I can talk about is we applied Alpha Evolve to discovering algorithms for matrix multiplication. And we did it by asking it to actually design kind of a search algorithm, a gradient-based search algorithm that looks for the matrix multiplication algorithms in turn. So it's a bit of a meta thing, like you look for an algorithm that finds an algorithm. But within that first algorithm, the search algorithm, we started from a really simple code skeleton, giving it basically nothing. We just told it use gradients, basically. And then it was able to write these complex loss functions and update functions, which had all sorts of tricks about penalizing various behaviors and introducing randomness in completely unexpected ways, which were like, okay, wow, this is the type of code that maybe a human could plausibly write, but would they have actually thought of writing this particular piece of code? That was really an aha moment, at least for me, that wow, this is doing something kind of human-like, but not something that obviously a human would try. So there is this idea called meta prompting described in the paper, where we actually ask our language models to propose their own prompts. So we just tell them what we are trying to do. Like, we're trying to do this evolutionary algorithm for improving on this particular problem, and we are going to prompt you with this particular prompt. But before we do that, please propose a modification to this prompt itself. And then we curate a set of prompts that actually work well for this purpose.
Could we touch on the benefits of program synthesis in general? So we interviewed Kevin Ellis recently. He's the guy who invented Dreamcode, a fascinating guy. He used to work under Josh Tannenbaum. And the way he described it, coming from a cognitive science point of view, is a lot of program induction is about explanation. It's about intelligibility. It's about legibility. And there was this incredible example when you were talking about doing the scheduling of jobs on, in Google's data center, and you've got this kind of matching problem and whatnot. And I think you said there was some previous experiments where you'd used like an inscrutable, reinforcement learning model or something like that, and it wasn't debuggable, it wasn't intelligible. And now you've got this beautiful 3 lines. But even then, there's the question of, is it legible? Have you found things that are not legible? Remember, there was that move 37 in AlphaGo, and that was a famous example of a discovery which was a little bit weird, and perhaps we wouldn't have discovered it, but maybe we understood it, maybe we could build theory around it. But when you look at some of these discoveries as well, are you finding deep abstract principles that you can derive from those discoveries? I mean, talk me through all of that.
Yeah. So you can span the broad spectrum, actually. So with Alpha Evolve, you sometimes discover algorithms that are really simple, and they're so simple that you can, like a human can verify that they're actually going to be correct on all inputs. And indeed, as you alluded to, they're so simple that you're just happy to submit them to production almost immediately, like no further checks needed. And it's in a completely different league compared to trying to deploy a neural network, which you have to think about things like retraining it and hosting it and the resources of running inference and all those kinds of things. So indeed, you can be in this very simple regime. For scientific discovery, you can also be in the regime where you explicitly look for programs that are interpretable. And you can do this by setting up the skeleton that you ask AlphaEvolve to fill in such a way that by design you expect it to be fairly simple. And we actually, maybe the clearest example is already in the fun search paper, where we looked for these big cap sets, like a specific mathematical object, and it found a function that we could look at, inspect, and we just noticed that, oh, this function is using the number 4 in this interesting way that whenever you look at the index in the for loop, you just look at the index modulo 4. And when you index into the array, you're indexing in at position I and I plus 4 and I plus 8. Like, okay, what's going on? And just by inspecting the code, we actually were able to develop, you can think of it as like a mathematical insight or a mathematical hypothesis. And that hypothesis turned out to be really crucial for then improving the results. Like we took that insight from the code, incorporated that insight into the next run, and we got much better results. So indeed, this can happen. But in some applications, maybe you don't care as much about interpretability, and then AlphaEvolve can develop even like very complex algorithms or a sequence of algorithms where you will perhaps not have the holistic understanding of how exactly this complex search heuristic works, but what you care about is the final result, and the final result is as good as possible.
So I'm curious about LLMs. I mean, first of all, let me give you my heartfelt congratulations on Gemini Pro. It is ridiculous. It's so good. Honestly, it's just I have no words to describe how good it is. But we're in an interesting time, right? Because in AlphaEvolve, you had an ensemble of Flash 2.0, I think, and Pro 2. And it just raises so many questions to me. What would happen if you did it with 2.5? Presumably internally, you have even better models that we don't know about yet. And how much uplift is there? And if you think about it, there's this Pareto curve of models, and Google's models are on the Pareto curve. So, we're trading off cost and latency and performance and whatnot. And if you were just using one model, there might be some optimal place on that Pareto curve in AlphaEvolve. I mean, maybe we should have a small model, but we should, sample it loads of times, or maybe we should have a big fat model, but not sample it as many times, or with an ensemble, maybe there's some perfect distribution of those models. But we really seem to have, especially with the reasoning versions of the models, we seem to have unlocked something which maybe wasn't there until relatively recently. Could you talk to that?
So one thing I can say specifically that is particularly exciting to me about AlphaEvolve is that it does get this uplift from improving the base language model. So this was not necessarily the case in FunSearch, but in AlphaEvolve we do see this, and we actually have a quantitative confirmation again in the ablations that if you also include the 2.0 Pro in the ensemble, then you get better results compared to just using the Flash model. So it's very clear that we are leveraging the kind of the frontier capabilities of these models. And of course, we cannot guarantee into the future what will happen, but at least for now, we are definitely riding the wave. So indeed, we're very keen in seeing how the base models improve and what kind of uplift the method is going to get with this together. The other kind of related point I would just quickly mention is that AlphaEvolve also offers this opportunity, which we haven't taken yet, but just forward looking, that it's a system that is able to enhance the capability of the base model. Like the capability of the base model is somewhere, but then this system makes it even better through orchestrating this test time compute pipeline, and actually so much better that you can make a new scientific discovery. So it raises the natural question, can we somehow distill this improved capability back into the base model? So that's something that you would get if you were to close the reinforcement learning loop. It's not something we have done with AlphaEvolve, but that possibility is clearly on the table.
Many of the programs it generates, they just fail immediately. They they crash. They're not valid programs. Those are kind of easy to filter out if you have an evaluator. And then at the opposite extreme, even once you've got those programs, say running the real world test case involves performing experiments in clinical trials, or a robot trying to navigate a complex field that may end up in getting damaged or something like that. So there's this huge gap between kind of automatic verification and expensive. And I'm just wondering, how can we bridge that in some sensible way for systems like Alpha Evolve? Just
Yeah.
curious, like if you have any thoughts on that.
Yeah, we are thinking about those things, and I think one thing that Matei alluded to before, with like this proving, like finding proofs, which is binary reward, and then you can try to ask LLMs for feedback to get like like some sort of shape reward to drive you towards the solution. I think that is a direction we're also thinking about, because indeed, like in many cases, you do have this kind of ladder of more and more expensive evaluation. Like for example, if you want to do some sort of simulation based as maybe for robotics, maybe for some like biology or physics or whatever, right? You can do some simulation based reward, and then like you ultimately want to try it in real world, and maybe it's like going to be again trying on a robot. Maybe you go to the lab, whatever. Like you do want, like, for every stage of this evaluation ladder, which is more and more expensive, you do want to have not just trying all the things that you found that work on the previous stage, but maybe have some sort of prioritization mechanism, which
Right.
can be can be LLM feedback, can be something else, can be like ELO scores. Yeah, those are the things we're thinking about.
Technologically, I think Alpha Evolve is already well set up for this. We have this idea of evaluation cascades, where you evaluate a large number of programs very quickly, and then a smaller number of programs you can spend longer to evaluate. So you can just expand this cascade all the way to the regime where maybe you can only afford to evaluate 10 things, and you actually have to go into the real world and run some real world experiments. But in principle, the mechanism is there. And I mean, this is what you have to do even if you try to solve the problems manually, or what
Sure.
actual researchers do. Like you have a finite budget. So first you try to filter the ideas using